feature talks from the teddy bear team from Ho Chi Minh City University of Science, Vietnam. Hey,
yeah, we're here.
Okay. Can you share your screen?
Yeah. Okay, I guess I will start my presentation. Okay, hello everyone. We are Teddy Bear. We are from University of Science in Vietnam. We would like to present our work on the SyntaGen challenge. Nowadays, the rapid advancement of deep learning and computer vision has significantly increased the demand of large and high-quality annotated datasets for multiple AI tasks. And the acquisitions of such datasets often require substantial resources, including time, financial costs, human resources, and many privacy reasons. In some specific tasks, there are not much suitable annotated datasets in the internet. So, to address our problems, the CVR workshops hosted the SyntaGen challenge. This is an interesting challenge. We participated in the challenge with an aim to introduce our solution. In our response method, our pilots includes three main phases. The first phase is to use a clip iterator to generate prompts for Stable Diffusion model by captioning real images. And additionally, we want to get a dataset that as much as same as Pascal VOC. So we decided to caption Pascal VOC images and feed the caption as prompts to Stable Diffusion model. The second phase is to use Stable Diffusion model to generate images from prompts. Given by the first phase, we chose Stable Diffusion 1.5 since the model tends to generate images more realistic and close to the images that captured by camera. For the setting, we chose the guidance scales at 8.0 and set 50 inference steps. And the last phase is to use a combination of a clip-like zero-source segmentation model and a classification model to generate semantic segmentation masks given the synthetic images and prompts from reverse phases. In the last phase, which is mask generation phase, the module includes two components. The first component is a classifier. The second component is a zero-source segmenter. We decided to use ClipES model as our final segmenter since it complies with the comparison rules and gives a decent result in our experiments. So why we need the classification component here? During our experiments, we observed that the pipeline does not guarantee the objects in prompts always occur in the synthetic images, which can cause redundant predictive masks in clip-like segmentation model. Our solution we use to address this problem is to utilize a multi-level classification model to fit out objects in generated image. The classifier includes two blocks. The first one is a feature extractor to capture the visual characteristic in the image. The second is a MLP block to grade prediction for multiple classes in the image. And to train the FC layers in classifier, we have prepared a dataset with around 18,000 images with labels. The accuracy of classifier for Pascal VOC multi-label tasks achieved around 97%. Here are some results demonstrating that the advantage of an additional classification model. You can see that it's clearly a win to have an additional classification model in our method. It helps to remove most of redundant masks from generated images. In the final submission, our dataset has 49 synthetic images and masks. The dataset achieved nearly 63 MIOU on the validation sets of Pascal VOC. And in rapid dataset, we are able to get more than 50 MIOU, we achieved top 1 result and significantly outperform all the teams. That's all. Thanks for listening our presentation. Thank you.
Thank you, the teddy bear team. Now we want to move next to the hot coffee team. Felix, yeah.
Hello, can you see my screen?
Yes.
Okay, nice. Hello, I'm Felix from the Hot Coffee team, and I want to present to you our submission to the SyntaGen challenge, and it's about principal component clustering for semantic segmentation in synthetic data generation. So let's get right into it. To separate from the related work, we are inspired by the authors from Dataset diffusion, which are the organizers of this nice challenge, and to separate from them, they average the self-attentions over layers and timestamps. And our idea and our research question was somehow how we get some semantic separation directly from the self-attentions without averaging and don't use multiple time steps to, for example, not only distinguish between like this classes like bicycle and window. We want to separate the class itself, like for example, for the bicycle, between tires, saddle, body, and so on. And to realize this, we have to condense the semantic information. And we do this by applying a principal component analysis to the heads. To explain this more in detail to you, I show you here on the left side the image, which is the raw stable diffusion output image for a prompt like a baby sitting on a yellow toy cart. And now we gather the self-attention maps headwise and apply an individual PCA to the features. And we reduce the features to 3 main components, and we map them here to RGB values for visualization, which is really nice. So you can actually inspect how the heads act. And for example, here on the upper left image, which is representing one head's features, you can see that the head focuses on, or the main components can separate the person, the baby, which is here presented in green, to the car, which is presented in black. And additionally, for example, the bottom heads can focus on the parts of the car itself. For example, you can see here in white on the bottom left image that the tires are indicated with this white color, and some other parts of the car have different colors, and even the face of the baby has a different color and indicates on different main components through the PCA. And this is really impressive because now we have condensed the headwise features, and every head can separate the original image into parts. But yeah, we want only one cluster map in the end. So we apply a clustering algorithm, K-means clustering, over all this individual reduced PCA feature maps, and we obtain something close to the right here, which gives us a mask for the baby in greenish, then the car in yellow, and additionally in some blue, some tires, and so on. But now, after we condensed all the semantic information, we lost knowledge about the class. And now the question is how to assign classes back to clusters. And to do this, we use the repository from Open Vocabulary Attention Maps, which allows us to compute some cross-attention for some individual text prompts without actually influencing our text prompt, which is given to Stable Diffusion. For example, our prompt to Stable Diffusion was a baby in a yellow toy cart. And for Pascal VOC, we have the classes person and car. And so we want the cross attention for person and car. And OVAM is able to generate us the class-wise cross attention maps. They are here visualized on the bottom right So we have a background class, a person class, and the car class. And as I told you before, we have this class agnostic clusters. And now with these indicators from the OVAM, we are actually able to classify the previously clusters. And we gather, like we obtained a very cluster or blocky label mask. And this is all done through stable diffusion, and we didn't use any additional information from the image space or additionally models, which there's no training on further models. But after the blocky masks, we use the image RGB values and relative position of the pixels to actually refine our blocky mask into a more precise and accurate mask in the end. Yeah, finally, our method is able to separate really, really well parts of the image. And for example, it can handle multiple class prompts like person and horse and table and chair. But yeah, unfortunately, we have still some ongoing challenges about assigning the correct classes with the cross attentions. We have some parts of uncertainty where we have some multivotes and we're not sure about the model. And so in the end, for our final submission to the challenge, we were slightly below the dataset diffusion baseline, about like 0.4 MIU, which is really sad, but still we believe that our method could really contribute to the state of the art because it's a really novel approach of collecting some semantic information through the self-attention map features. So yeah, finally, that's it. I want to thank the authors of the dataset diffusion paper and additionally the open vocabulary attention maps. And if you have some further questions, you can contact me via mail or directly add me on LinkedIn. I'm always open for a nice discussion if you have any remarks or something. And finally, I have to thank my sponsor, Aptiv, to fund my PhD. So yeah, thank you very much.
Thank you, Felix. Next, I would like to invite the Best Paper Award presentation.
No.
Did you talk to me? Sorry.
No. You can see that.
So to conclude again. Okay. So to conclude finally, is synthetic data all we need? Well, not quite yet. Synthetic clones are more vulnerable to adversarial perturbations and common corruptions compared to models trained with real data. And they're also worse at detecting out-of-distribution samples and are not as well calibrated as models trained with real data. This shows us the way for creating better synthetic clones. In our paper, we show certain ways which can make these synthetic clones more robust using additional real data or by changing the prompt type for generating these images. If you're interested, please check out our project website or read our paper. Finally, thank you for your attention, and I hope to see you at a poster session at 11:40.
Yeah, okay. Cool. And I share, right? Share screen. Microsoft. Okay. Presenter. View. Oh, okay. Okay, great. Sorry for the delay. Okay, hello, my name is Xiaodan Du. Today I want to present our new work, Intrinsic LoRa. It's a collaboration between me, Nick, Greg, and Anand. Large-scale generative models, including autoregressive models, GANs, and diffusion models, can produce high-quality, hyper-photorealistic images. These models may seem to have increasingly sophisticated understanding of the three-dimensional world. And our work is about testing to what extent this is true and how that knowledge can be extracted from the models. In this paper, we hope to explore and answer two main questions. First, what underlying knowledge is presented in different types of generative models? And second, can we find a unified method that can extract this underlying knowledge easily from these generative models? To answer these questions, we propose a LoRa-based method named Intrinsic LoRa and conduct thorough studies of what it can do. I'll now go over our findings one by one. First, the method proposed, Intrinsic LoRa, or iLoRa for short, is capable of extracting various intrinsics across a broad spectrum of generative models. Our method, Intrinsic LoRa, can extract image intrinsics from all kinds of generative models, including autoregressive models, GANs, and diffusion models. Here, I use stable diffusion as an example to illustrate our pipeline. So we start with a frozen pre-trained unit and initialize LoRa adapters on top of its attention layers. During training, input image is encoded and the clean latent embedding of an image is passed in the network. The model accepts a text input, which is not important for our task. We input the name of the intrinsics, for example, surface normal as the prompt, but it really can be anything. We then encode the ground truth intrinsic maps into latent and minimize the MSE loss between it and the predicted latent. We use the supervision to update the LoRa adapters with everything else kept frozen. Thus, the UNet here is repurposed into a dense label predictor instead of a noise predictor. During inference time, given an input, its output can be directly decoded by the original decoder, treating intrinsic maps as a special kind of image. The same method can be used to extract not only surface normals, but also depth, albedo, and shading with dedicated sets of LoRa's. Here are the scene extraction results. Everything good? Can you share? Oh, they're not seeing it? Oh, I see. Okay. So, sorry about people on Zoom. Sorry about that. So here are the scene extraction results from different models across different domains. So we now move to our second contribution. Training of ILoRa is highly efficient, requiring only a small number of new parameters and samples. So please refer to our papers about more details about this part. We only need a couple hundred images to train this LoRa adapters. So to me, one of the most interesting findings of our work is that the quality of the extracted intrinsics is correlated to the quality of the generative models themselves. So here we show two graphs. We apply ILoRa on 3 different generative models, VQGAN, StyleGAN V2, and StyleGAN XL, that are all trained on FFHQ dataset. For both surface normals and depth prediction, error rises with the model that has higher IFID scores. This correlation holds true for a broad range of error metrics. We are showing 5 of them here for both surface normal and depth. This observation of the correlation between the quality of the generative model and the accuracy of the extracted scene intrinsics remains true for Stable Diffusion UNet as well. We conduct an ablation study of various Stable Diffusion versions. Our analysis includes a randomly initialized UNet, that's the third column from the left, and Stable Diffusion versions 1.1, 1.2, and 1.5, each demonstrating significant enhancements in image generation capabilities, which in turn improve the fidelity of scene intrinsics extraction. So finally, the 3 main takeaways of this presentation. First, generative models implicitly learn physical scene intrinsics. Second, tiny ILoRa adapters is able to extract this information with little additional effort. Last but not least, more powerful generative models give more accurate scene intrinsics. Thank you very much for listening. For more information, take a look at our paper, project page, and GitHub repo. If you have questions in the future, my contact is to the bottom. Thank you.
Can you hear me okay? Good. I think what I plan to do today is give a little bit more of a historical perspective. And as I age, I feel I end up doing that more and more. But when I look back over 25 or 30 years since I've worked on generative models, a lot of the early work was really concerned with how we regularize inverse problems and how we learn representations, essentially trying to disentangle the sort of different causal factors of variation in data. And the idea that you could use a generative model to produce a high-resolution image seemed really far-fetched. And in fact, if you had asked me 25 years ago, I would have said not possible. It was so hard. And then everything changed about 10 years ago with VAEs and deep autoregressive models, and in particular GANs, which were really producing amazing images. And again, just in terms of a sort of retrospective view, if you look back, the images actually don't look that great. But at the time, we were pretty excited about it. We thought, wow, we've really nailed it. And this led to a lot of research in the area, and work in particular on GANs really progressed very, very quickly. And they became the model of choice with, and some of these have already been mentioned, style GAN, big GAN, et cetera. And over the last 2 or 3 years, diffusion models have really, in some sense, unseated GANs as the model of choice. And in our group with my team at Google, we started working on diffusion models for image-to-image translation. And we're first really interested in this task for image super resolution, where we were trying to use magnification factors of up to 16 or higher, which really are fundamentally a generative task. And then we moved on to multitask models and a much wider range of sort of image-to-image translation tasks where the ability of diffusion models to really capture complex multimodal distributions on high-resolution images really shined. And from that, we started working on text-to-image models, which seemed like a really natural step. And again, we sort of we were trying to get to really high-resolution models, and it didn't work that well until we started using cascades. And with cascades, we could grow these models and generate up to 4K images, for example, like this one here, which again was pretty stunning. And then we moved on and started to work on video models. Okay, so and the progress has been amazing, but there remain various questions, and it was actually great to hear some of the talks before this one, because a lot of these talks have introduced some of the questions that I wanted to ponder a little bit in the talk today. And one of these questions essentially is, well, how good are these models really? And what else? And I guess what else I mean beyond simple content generation, what are they good for? And the standard performance metrics, and we've heard some of them mentioned already this morning, like FID and inception score, are very good, and they've been great at tracking the progress of generative models over the last 5 years or so. But it's well known that in some sense, they're not necessarily extremely highly correlated with human perception. And in particular, while we use FID often as we do hyperparameter sweeps to really try and find good parameters for generation, we eventually throw out FID and we use human evaluation as the arbiter of good models versus bad models for the most part, because FID in the end don't really correlate well with human perception. So an alternative way to begin to evaluate models is actually to consider how they perform on downstream tasks. And so the idea is that if your generative model has really captured the true distribution of your data, then expected performance on downstream tasks should be the same under the model and actual training data. Or equivalently, whether you train your model on training data or synthetic samples shouldn't really matter that much. The other thing you would expect is that if you were to augment your real data with synthetic data by mixing it, performance on tasks should generally get better. And it was really, and of course, data augmentation has been used extensively for many years, even going back to some of the earliest work on MNIST character recognition. People were using all sorts of augmentations of shifting image, cropping, elastic deformations. And one of the real questions for generative models is, are you able to generate data that actually performs better than all of these manual augmentations that people have worked on for many, many years? And with this backdrop, Ravuri and Vinyals came up with this idea, and they called it the classification accuracy score. And what they proposed, this was a way to evaluate generative models. And what they proposed is, well, what we should do is look at downstream tasks. We should take the best models. We should generate data, for example, from a model trained on ImageNet, and then we should train an ImageNet classifier using generative data, but test it on real data against a baseline model, which was also trained on real data. And they prescribed a protocol for doing this. And the protocol involved use a ResNet 50 trained for 90 epochs, I think it was, use center crops, etc. So that you were always doing apples to apples comparison between models trained on real data and models trained on synthetic data. And when they did this and they applied it to what were at the time the state-of-the-art models, they got somewhat disappointing results. And in particular, looking at like top one accuracy, while a model that ResNet 50 at the time trained on real data attained a top one accuracy of about 73%. VQ-VAE2 and I think it was just a minute. And Big GAN significantly underperformed. And you can see this if you look at accuracies class by class. And so these were two plots from their paper showing I think the GAN on the left and VQ-VAE on the right. The blue dots are the accuracies of the 1,000 classes of the model trained on real data. And the red dots are the class accuracies for the models trained on the synthetic data. And they fall short. Then they also looked at generative data augmentation. What they did was they say, what if we mix synthetic data with real data? What happens? And the answer was it hurt performance. Even adding, a moderately small size of synthetic data really hurt the performance of these models. And the only models for which they got a little marginal boost in performance were the GAN models with a very small truncation parameter, where in essence, what they're doing is sacrificing the diversity of the samples for the image quality. And with sufficient image quality, but limited diversity, they got a little boost in performance, but then performance degraded again, ostensibly because of bias in the data set itself. And so despite the promise of generative models, at least as of 3 or 4 years ago, it was actually relatively hard to find a good example of a generative model that could produce images that would really improve performance on fairly complex tasks. And as such, it led to a degree of skepticism in the community. Okay, so, and now what I want to do is just talk about a couple of different examples of generative models that we've played with recently that I think show really promising performance. And the first, historically, it's a version of a variational autoencoder. It was a project led by Sajjad Nuruzi in my lab at the University of Toronto. And the idea was to come up with a model, a non-parametric, latent variable model where in order to generate an image, what you would do is transform exemplars from your training set. And so the idea would be that you would take in an input, and then from your generative model, it would be able to generate a variety of different outputs. And the key here is that by learning the right structured latent space, that would control how meaningful the transforms or the transformations were. And so the structure of the model looks something roughly like this, it's a little like a memory augmented VAE. So you store all of your exemplars from your training set in memory, and what you're actually storing are their encodings within a latent space. And then you have, and then we imagined at the time a Parson window estimator, which provide us a density function over the latent space. So effectively, it's like you could imagine a mixture of Gaussians within the latent space. And so in order to sample from the model, you would first randomly choose an exemplar, and then you would perturb it in the latent space, and then you would put that through a decoder to get your output image. And insofar as the latent space learned a well-structured representation of the data, these perturbations in the latent space would be meaningful. And then the way the model is trained is with an evidence lower bound, except rather than the usual Gaussian prior in the latent space within the KL term of the elbow, we just have this large Parson window or kernel density estimator as the prior. And to get this model to train well, there were a variety of regularizers that had to be included to avoid totally degenerate solutions, but the net result turned out pretty good. So what I'm showing here are sample generations from a model trained on Syllabe and another model trained on MNIST, where in the upper left of each block is the exemplar, and all the other examples within that block were synthetically random samples from the model. And so the samples looked pretty plausible to us. And the other thing we found is that with this model, we got beautifully structured latent space representations of our data that really, for whatever reason, separated the different classes really well. Here on MNIST, much better than a conventional VAE with a Gaussian prior. And so even simple nearest neighbor classifiers worked extremely well on this. But what got us really excited was what happened when we did generative data augmentation. So in this case, what we did was we trained a simple MLP. And the way we did it is within each batch, for every real data sample, we would generate one synthetic sample. So it essentially doubled the size of the data set. And then they were weighted with a cross entropy loss. And in fact, we found that the synthetic samples were so good, we actually weighted them higher than the real samples. We did a sweep over the weighting parameter, but what we actually did was we weighted the negative log likelihood of the synthetic samples by 0.6 and the real samples by 0.4. And then what we found was that compared to, the state-of-the-art models with simple regularizers like label smoothing, which got sort of, accuracies of about 1.23%, or error rates of about 1.23% on ImageNet on MNIST, the model with the data augmentations dramatically dropped the error rate down to something very close to the state of the art. And when we went just one step further and we expanded the number of units in the hidden layer, the performance dropped even more down to an error rate of 0.69, which, as far as I know, is the state of the art in permutation invariant MNIST. And in particular, the state of the art above all the other techniques that people had developed with manual augmentations at the time. It didn't really work well when we tried it on ImageNet-like samples on higher resolution images and with greater diversity. And while in many ways we should have pushed on it harder to see what it will look like, and in fact, this model bears some resemblance to diffusion models today. At the time, we had already started working on diffusion models, and the first model that we were playing with as a generative model in the space of diffusion models was a cascaded diffusion model. And what that model did was basically combine a low resolution ImageNet based model that Jonathan Ho had been working on at Berkeley, which just generated class conditional 32 by 32 pixel images. And it combined that with our super resolution models that I mentioned earlier in the talk to give us samples from ImageNet at 256 by 256 resolution. And we were pretty excited about this because, among other things, it did great on FID and inception score. And even more excitedly, it really made a big bump in the quality of our classification accuracy score. And in particular, what it did was it took the gap between the previous models and the baseline model, and it cut it in half. So all of a sudden, we were getting 63% accuracy on the classification accuracy score. Okay, so that was great. But the bad news was when we tried it with generative data augmentation, it didn't really help. It didn't hurt performance as much as some of the previous techniques, but it didn't help dramatically. And still, there's a big gap between 63% and the 73% baseline. And so what we started to do just over a year and a half ago is to push on this a lot harder. But we wanted to do this changing the rules of the game, so that a lot of the work in generative models that went on over the last 15 years or so, the rules of the game were that you would train your model on a prescribed data set like ImageNet, and then you would test it on held out samples or with various metrics of performance on that data set. And what we really wanted to do was explore the idea that foundation models might be the right path forward for generative modeling. And this will come as no surprise, I think, to anyone in this room right now, but to us, this was a bit of a leap that we were going to change the rules of the game. And indeed, when we first submitted this paper, we got slapped on the hand for changing the rules of the game. They said it's not fair because what you're doing is you're taking a large foundation model and then you're fine-tuning it on ImageNet. And indeed, that's what we did. So we started with the Imagine model that I mentioned earlier, and we wanted to see how well it could generate synthetic samples that would help us in ImageNet classification. And to that extent, the first problem we ran into was that the class names in ImageNet are much more specific than those words in daily use, in open vocabulary context. So words like trunk or chest have multiple meanings, but in ImageNet, they really only have one of those meanings. And so there are a variety of ways of handling this. One way that people have handled this is through a prompt extension, variations in prompts. Another way to go would be to take your ImageNet images and do prompt inversion to get back prompts that would have generated images within the ImageNet training set. What we did was I think what is the simplest approach, which is simply take ImageNet labels and images and fine-tune the Imagine model on that data. And to do that, we had to be very careful with our choice of hyperparameters to get the right things. And among, just as one example, typically for Imagine to generate the best quality images, we used a very high guidance weight in classifier-free guidance to get Imagine to generate really nice looking images. But what we found here for ImageNet is that we were much better off using much smaller guidance weights. And I think the reason is fairly simple, which is that ImageNet classes are very diverse and the images are generally fairly small. The resolution, the fidelity of the image is not that great. And so we didn't need really high guidance weights to generate high quality images. We were perfectly fine with very low guidance weights, maintaining diversity with sufficient image quality. And then once we fine-tune the models, this is an example with 4 classes, where on the left you see images generated from a prompt that was just an image of X, where X is a class name, and you'd get great diversity. But typically the images really didn't match the distribution of the classes in ImageNet. And what you see on the right are the images we got once we had fine-tuned the model. Here are another set of images we got once we had fine-tuned the model. Now, one of the results, which is kind of interesting at first glance, is that the FID scores and the inception scores are hugely better than anything we had previously. But on the other hand, we're training on 100 times more data. The pre-trained models prior to the fine-tuning were trained on 100 times more data than the ImageNet data. And so it's really, I don't think it's terribly surprising that we get much better numbers. But what is interesting is that we go look at classification accuracy score. So the baseline model that gets 73% is shown by the horizontal line at the top. And the cascaded diffusion model that I talked about earlier got around 63%. And then what we find now with the fine-tuned Imagine model, we're up to about 70% classification accuracy score, really significantly closing the gap to baseline. And if we want to look at class per class accuracies, here is what we got with the cascaded diffusion models. We get a few classes that seem to generalize better than the model trained on real data, but not very many. Here's what we get when we looked at the fine-tuned Imagine model. So now we see many ImageNet classes generalizing better to the test set that were trained purely on synthetic data. And from there, we moved on to look at generative data augmentation. And so for this experiment, what we did was we generated a data set that's twice as big as the ImageNet training set. So it's about 2.5 million images. Half of those are synthetic, half of those are the real data. And we took 15 different architectures, convolutional architectures, transformer-based architectures, and we took the training methods that were specified by the authors of the respective papers that got them the best possible results. We validated those results using the same training protocols on the real data, and then we trained them the same way on this larger data set. In every way, we trained them the same, except we gave them more training time. And in every case, we saw a major boost in performance, which was really great. And then finally, you can ask the question, well, what if rather than doubling the amount of data, we triple it or quadruple it? What if we go out to 10 times more data? And so we looked at this both at several different resolutions, but what I'm showing here are at a resolution of 64 by 64 on the left, and at a resolution of 1K by 1K on the right, and with top 1 and top 5 shown above and below. And what you see at 64 by 64, the model gets better and better and better as you add more and more data. And I think this makes sense to some extent, that when you downsample the images very significantly, you're taking away a lot of information from the real data, and now there's more room for the synthetic data to make it up. At 1K by 1K, what we find, so just again to ground you, on the far left of this plot is the situation where we're only training on real data, and that's the 64 by 64 result. The result at 1K by 1K showed a boost in performance even by adding up to 5 times as much synthetic data as we had real data, which was pretty good. Okay, so back to the the earlier slide. So how good are the models? I think the models are getting better and better and better. And again, that's no surprise to everyone here. And what are they good for? I think they're good for all sorts of stuff. What I've been focusing on here is using downstream tasks and data augmentation with a prescribed protocol that really allows us to measure how well these models are doing as they progress. And I think we need more and more tasks that we can evaluate models on. And several of these tasks are already out there. What we need to do is just formalize them a little bit more, but there are fantastic results on, for example, contrastive learning by Yonglong Tian and Li Jifan, for example, got some great results on contrastive learning, and there are many others. And I expect these results are going to continue to get better and better and better. And just to give you a sense why they're getting better, and one of the talks this morning was talking about 3D. So one of the things we've been working on are models that from a single image can generate in a controlled way multiple views of scenes over time or with different camera poses. And I think there's a lot of excitement in this space. The idea of 3D and 4D models is the next frontier. We've been developing ways of getting rid of cascades to simplify the training pipeline, and we now have methods that will train up to 1K or 4K images as a single stage pixel-based diffusion model. And it just requires careful thought about the architecture and the training procedure. We're really interested in how we can fine-tune models in different ways, and in particular, how we fine-tune models with different reward functions. And in some work we just presented at iClear, we've been using LoRa's and gradient-based fine-tuning on reward functions, essentially backpropping gradients through the sampling process that allows to take images like that and produce more complex, more interesting images. I'm out of time, I guess, huh? Okay, I've got lots more slides, but I'm going to stop there. The one interesting thing, sorry, let me skip over this. One interesting I wanted to mention, which is also really closely related to one of the talks earlier this morning, is that one of the things we're finding is that the generative models do tend to produce representations that seem incredibly well aligned with people. And so what this plot shows are for about 60 different classifiers, VITs, convolutional networks, ResNets, VGG, you name it. What this shows is the extent to which they make the same errors on 17 different out of distribution data sets. And what you see is that in the top left 60 models, they all more or less agree on the errors they make in out of distribution data. And these are all discriminatively trained, some of them based on CLIP, etc. What you see in the lower 10 by 10 grid are 10 people and the degree of correlation in the errors they make on the out of distribution data. And the final two rows are basically classifiers based on Stable Diffusion and Imagine, and they really agree much more closely with sorts of errors that humans make. And with that, let me finish. Let me close by thanking you for your attention and by thanking all my wonderful colleagues who did all the work that I'm talking about today.
I think we have time for maybe one question only.
I'm also going to be around all morning, and I'm happy to talk to anyone. In fact, I'm around all week. If you send me email, I know I've taken too much time, but
You can use the mic over there.
That's it. I'm gonna see a blue screen over there. Okay. All right. Okay. All right. Well, first, I'm really glad to be here. I think this talk may be a little bit of a pivot from normal talks that you're used to. So I'm going to talk a little bit about like how things have changed inside a big corporation as these large models have come about. And, hopefully it provides some insight in future research and also sort of the challenges and, where things may be headed and sort of what it feels like maybe inside a large industry. So first of all, I'm from Adobe Research. So we do all kinds of research across a lot of categories and topics, many papers at CVPR. You saw some ones earlier in the session. My particular background is in 3D computer graphics. This is actually my first time to CVPR. I'm typically at SIGGRAPH and some of the other venues. So I'm really excited to be here and be part of this community and get some more experience on this topic. Yeah. Let me see. Okay. Is there a way to... So back starting in mid-2022, the large image foundation model started to crop up, the sort of things like DALL-E. And Adobe, like many other companies, sort of started going this route. And so in research, we started training this new model, which is called Adobe Firefly, which many of you are probably familiar with. And this began sort of mid-22 to mid-2022. And then we were able to first ship it in March. And what I have to say is like, everything changed like inside the company, everything. And I'm really curious to hear like how things were at Google and other companies, just the feeling of like what it meant to go from like how we traditionally delivered software to all of a sudden now we're having to deliver these really, really large models. So for those of you who are familiar with the general practice of how we go about doing research in these types of fields, the pipeline to success that many of you are familiar with is you go out and you collect a nice data set. Maybe there's a data set already out there on the internet that's for you, and you can just collect it, run some cool data processing on it. Then you run some cool training algorithm. Yay, you have your CVPR paper, everybody's happy, and you reiterate this process. Now, this is not how it works inside of industry. So I want to go through a little bit of this pipeline of what it feels like being inside an industrial research lab. So this is kind of what the life cycle looks like inside of a big company. So it's going to start with raw assets that come in, and these could be like internal assets that either come from like stock collections, like Adobe has a large stock collection of image data and video data. It might come from user data that's come into the company. It might be from external purchase sources and acquired. So the first step of the process, right, is to start training your algorithms, right? Wrong. So you have to go to the legal department. And this is actually a big challenge. They're going to actually look through everything and make sure that all the copyright, the licensing terms, and privacy is all set and good to go. And there's many data sets which are fantastic out there, but we just can't touch them for many obvious reasons. So once these assets are legally approved, they're going to flow into what we call the moderation pipeline. And so what is moderation? Well, moderation is really a filtering pipeline. And for those of you who want a lot of data, it's like, oh no, because it's like takes this big data set and makes it smaller. And what it does is it looks through and scans for things like brand and copyright and trademarks and not safe for work stuff. And this actually entire moderation pipeline requires humans, but it requires vision tasks as well. And so there's actual research that needs to go into figuring out how we moderate data better to make sure there's nothing in those data sets that really shouldn't flow on to the next stages. So after we have these moderated assets in, it can flow into a factory. And the factory here is like a lot of what we discuss in this conference, and I see the discussions earlier. It's like, how do we take this data and like reorganize it, combine it in different ways, mix synthetic data along with real data in interesting, novel combinations, and package it. And there's also a lot of effort that goes on in like, how do we package it in a way that we can deliver it to the training nodes at scale in real time to go as fast as possibly can to actually train the algorithms. So there's actually teams and efforts and code bases just on optimizing these assets for delivery at training time. And plenty of research that needs to go into actually improving the efficiency there, because that's actually a large part of the cost. And then finally is this little part of training, actually. And I would say like this training aspect is becoming a smaller and smaller slice of the pie. Yes, we iterate and do the training, but a lot of the work, all this work that leads up to training is quite significant. And then finally, after you have a model, you think, all right, you're done. Let's ship it out to customers. But actually, this is just a candidate model, and it has to go through what's called an ethics and bias review. So this gets, the ethics and bias review actually goes to another group inside the company that actually runs a human evaluation, and they also have automated scripts to try to figure out, like, is there significant bias or harm in this? And there's an ethics committee that actually looks to say, all right, can we put this model out, and is it going to cause any problems or issues? Now, at that point, you finally have this approved Gen AI inference model that's like, all right, good to go. Well, not quite yet, because it needs to be distilled down to actually run and optimize. And so there's a continual distillation process to actually squeeze down the weights, make it run more efficiency, because once you deploy it in the wild, it's going to incur costs. So this is a massive pipeline requiring lots of people, lots of teams, lots of individuals working on all kinds of different components all at the same time. And communicating across this huge, enormous pipeline is really, really hard and really, really challenging. And I'd love to know how other companies do it, because it's something we're learning and struggling to figure out. And I see some smiles over there from some people in the crowd who may be familiar with this. It's not as easy as one would think. And so this is like a big, like, I think of like a factory assembly line that you're like, these like goods are moving from left to right and flowing through the system. And then the moment that there's like a hiccup, there's not enough moderation team, or the legal team blocked or stalled, everything halts and everything slows down. The other thing is that things are constantly changing, like laws change, and all of a sudden the legal team says, oh no, we can't use that data. So this data set's no longer a viable data set because of legal changes that may occur. And so that then requires a new search to go figure out, all right, now where do we get a new data set to fill this gap or hole that we have? Moderation may like subset your data down, so you just don't have enough in your distribution to make things well represented. So now you're like back at the beginning trying to figure out, all right, where do we get more data from to sort of fill this domain gap so we can get good results? Training time, you also discover that your model's not learning well for task, and so you just don't have the right set of assets that you need to do the learning, and you're not getting the quality that customers would want for the feature that you want to release. Finally, there's ethics and bias stuff. You find out that the distribution of data just is missing in certain categories, and that you can't deploy the model for various reasons, that it just doesn't pass the test and the sniff test of what's right and proper and ethically, what's ethically right. And so you need to have like more data of a certain category so you can generate better quality and handle those types of distributions. So anyway, all of these things cause kickback in the pipeline, where you have to like do a reset, start over, and then the data has to flow all the way through, and you have to retrain the models, and it invalidates everything that you've done. So meanwhile, along this entire pipeline, there's sort of parallel efforts that are going too, where like as a researcher in a company, you're like, oh, I have a cool idea. I can do intrinsic decomp from my generative AI foundation model. Maybe that would be really cool for a product like Photoshop or one of the imaging products. And so it's like, I have this cool idea. I'd like to do it. I want to use this vision model. So we start doing prototyping, and we start grabbing and building on top of these foundation models early on, and we start validating with users. And then interfaces get designed, and then finally things get integrated into product. And finally, at the end of this very, very long and arduous, painful process, things can finally ship out to customers where you have a deployed service in the cloud that's happy, a product integration with a good interface. Now, this is a lot, and this requires like large, enormous teams working on all kinds of different tasks and the levels of coordination and communication. And then finally, I should say, like, even when you get a feature out, there's kickback of like, this isn't good enough. We want more, or the resolution, or the types of assets. Like, this is too cartoony or too photoreal, or we need more of this or that. And this then just puts back pressure on getting more assets. So what do we do? And what are some of the things that we've been thinking about? Well, this conference is all about synthetic data generation. And so one thing that you realize is that if you have legally approved assets through the pipeline and they're moderated and everything's good, you can recombine them in interesting ways. And that means that if you find later in the pipeline that you need more assets or more data to improve your models, you can just go back to the factory and just work and iterate and recombine them and try to iterate on improving the data, the training data, just in the factory itself without having to go all the way back to find and purchase new assets out there in the world. And sometimes, as we know, that assets just aren't even purchasable. Like, I work in 3D, and there really aren't that many collections of large 3D models out there to be had. And so if you want 3D data, you're going to have to somehow make it, synthesize it, or combine. And I'll talk a little bit about that later. So I want to do like a final kind of quick case study on the 3D side, since I'm a 3D person. I see the size here. He was like one of the people on this work. So I'm going to talk briefly about LRM. So we've been working on this large 3D reconstruction model, and it's a way to sort of mix imaging with 3D to sort of leverage the best of both. So we know that we have lots of images and video data, and we all have very, very limited 3D data. And so the idea here is you can take a large foundational model like Firefly or an image model, and you can fine tune it to do multi-views. So in this case, you can take a text prompt like a dachshund wearing a boater hat, and you can generate multi-view images. So here's our multi-view example of this dog, and you can feed it through a large reconstruction model, and then which is a separately trained large foundation model. And this will like fuse things into an output. And this can be a radiance field, which could be a mesh or a Gaussian splat. I think in this case, it's a mesh, but we also do Gaussian splats and NeRFs. So there's many different formats that this can go to. It's nice because it mixes the data that we have, that we can get 3D data. Is this on or off or on? Anyway. Did this just turn off? All right. So this is nice because it mixes the different types, distributions of data. So we have a lot more images and video data with very, very sparse 3D data. So the way this model works is we take our image and we tokenize it into a large transformer network. And this, in broad strokes, sort of turns and it gets tokenized, and then we're able to output a radiance field from this simple model. And so it's about 300 parameters that went into training this. And we used, at this time, this was early research exploration. So we used Objaverse and NV ImageNet. And with 1 million multi-view assets, we were able to train several models. And this led to a succession of papers. And you can go look them up if you look at LRM online or Instant 3D or PFLRM. These are fantastic papers that sort of follow this line of thinking and reasoning. And we see this followed. Many other industries are starting to look or use this similar route to get to 3D. And I think David actually alluded to some of that in his talk, directly learning 3D and 4D from image and video data. So you can obviously extend this to videos and multiple images and views input. And here's just some quick examples of the types of results that you can get today by taking, say, 4 images in and get one of these output radiance fields. And this is 3D Gaussian splats. You can also do this for full scene data. And so this is just a reconstruction that actually happens in less than a second or so. And it builds a full 3D radiance field that then you can fly through, which is pretty exciting, just from 2 input photos. So one of the questions, though, is now we have these academic data sets, but these really have a lot, are not something that we can necessarily take and go to production with. And so what do we do? So we've been running some internal experiments to see, can we just synthesize 3D data in interesting ways? And do we really need semantically based data? So given these input images, we have our original LRM model where we can actually do a 3D reconstruction. And we can also feed this into a different, the same model, but it's trained on what we call Zeroverse. I thought it was a very clever name, which is really just a combination of 3D assets that are like mixed and matched and composed in different ways. And you can see the example here. There's nothing semantic about it. And it turns out that for this particular 3D reconstruction task, we got similar results to actually using the more semantic-based data sets that came from the Objaverse training set. And so it's a really interesting way and clever way to sort of mix and match. And clearly the Zeroverse data set doesn't have the legal implications. It doesn't have the moderation issues because it's purely synthetic and semantically meaningless. And yet it can be useful for low-level vision tasks. So I want to just conclude with final thoughts. The pipelines inside of large companies just continues to increase in complexity. And I think getting software out the door is going to be really, really challenging. I think each of those stages of the pipeline pose interesting problems. Still inside a company, we send data out to be labeled by humans, reviewed by humans, analyzed and assessed by humans. And it'll be really interesting to see, can we get to vision tasks that can do it? I'll give you one really fun open challenge. We thought, like, how do you moderate 3D data? So like, is a 3D asset like safe and safe for work, for instance? Well, you realize quickly that you can take any 3D asset and put a box around it. And if you just render it from different views, you're only going to see the box. And so now do you need to have like deep shape recognition inside your 3D moderation pipeline? I mean, these are some very interesting conundrums and difficulties that get faced. And the total cost of scaling these developments, increases with these large scale models. And so we need to actually start thinking as a community, basically how do we address and automate and apply vision and computer vision tasks to actually help with all aspects of the pipeline and not just at the moment of training. So with that, I want to just thank the Adobe teams. I have many collaborators, many researchers that all led to the Firefly work and then the work, some of the work that I showed on the large reconstruction model.
So we have time for one question from the audience.
Everyone, jumping from University of Maryland. So, previously I was thinking about the word what I was to reflect my my top letter, guide for the line spectrum generator. So over probably a year ago, that segment energy model over my mind. This is the first time I see that the future models that work so well across the board, different type of data and then different text. And the really secret, like this is the first time I really believe that completely that the data is the key. So you can see the training data that they have is really kind of orders of magnitude over the one, including the I guess the user side, but also the annotation. So the most interesting thing, aside from like performance, is that it has a strong zero-shot generalization ability. So if you look at it works remarkably well for images for outside the image defense. So it's very probably when you scale the data sufficiently large, then the interesting property emerge. And this is not just the one single example, like there are many other successful stories in the community that if you turn on large scale data, then you will get more generalized performance, such as like dynamic view and things, right? So, but if you look at kind of the data, the fuel that drive these models, they are all kind of millions of like images, macro images, and images, or sometimes images and text pair. So, but it's really hard to kind of scale it up, as Nathan figured out. Like, it's really hard to get there, like all this kind of training data. Like you need to go to outside, you need to go to approval, review, and make sure that you don't have bias and copyright content and so on. So it's very, very difficult to do this. But if you already have the kind of collection of data that really works well, then you can simply train this model like a text image generation model. And that's what we see today, like a text image model obviously everywhere. Yeah, so and you can see that all the kind of major players in the field, they all have like very strong like a text image generation model that where they just put in pretty much remote text and generate like really amazing images. So I was really blown away by all this kind of process. So, but if you look at the kind of, and this is actually not just useful for generating for images. For example, you can actually have several pieces of work that try to use this kind of text image generation model to learn visual representation. So, for example, you can take a text training data set or human text, and then take a generate the CNN of images using different data generators, and you can try learn a model that can generalize very well and very competitive. So, and you can. I mean, sometimes you don't even need to have humans to write the text. You just use the LLM to write text. I think maybe this was later on. We'll talk about some of this after. But it's very cool. Like you can actually train only on synthetic data, and that resulting in presentation that really works really well for downstream tasks. All right. So now this bottom line is really about how well does this generator work. So we look at some of the examples and see like what are the major things there. For example, here we ask the generator to generate some full apples on the table. But it's like the image quality is very good, but it doesn't really know how to count, right? So maybe it's latency problem that we try to cherry pick, but to try many different examples, it still doesn't know how to count. And it's not just for the latest, greatest generation model, but also across the part 4. So I can also test on the journey and use from Meta. And along all of that results, they all come to wrong thing. So they don't really like the full end thing. Another example is like a spatial composition. Like if I want to take those models work really well in just one particular job, and it works very well. But if you just say very simple things, like I want to dog sitting on the left side of the chair, like Dolly 33 generating results, and we generate a new model data. They all have a dog and chair, but the dog we used to see on the by the side of the chair. The chair is clearly more common. So it's pretty hard to get this model to behave what you want. So it's hard to align our retention. So therefore, it's going to be hard for people to take them there. All right, how do we solve this problem? Of course, you can try to see. Let's say just collect one lot more data set, right? So just collect more images and go through the process. And then once you have all this data set, scale data set, and then you can go further. But the problem is that, like, as in the industry has hundreds of thousands of statistics get from the web. But we use the statistic at in university, we always kind of struggle with the kind of GPU. So it's really hard. And this is kind of the difference between GPU 3 and GPU 4. And this is actually known as the so-called Generative policy. So this is obviously I want to say this is open guide exploration. So we really want to see whether we can break through this gap, right? How do we survive? Okay. So this is how zero job. How do we make the model align with ourselves, with our intention better, so that we create better results here. All right, without doing all the spending and different data. All right, so I was kind of structured talking to two main projects that come out in my lab. One is like to focus on single image. That if I only want to generate a single image, what can I generate something? All right. Well. Okay. Okay. All right. So can we generate single images that align well with our text font? So you can see that now all the documents are deployed and Apple is like forward. So this specifically content. So this will focus on more on the how do we get the existing recurrent text-based models to have this conversationality capability. On the other hand, we'll talk about some preliminary results on how we generate multiple images. And we have some specific application in mind. And this there, that multiple images here, interesting is how we can generate more consistent results. All right. Okay. So let's go to the first part. All right. So how we get the model to enable conversationality. So one way to do this is very simple. Let's say I want to generate a cat wearing the center hat and star in the snow, right? So how do we generate make sure that this image is really aligned with my font? One way to do this is to do grounding. So if I have I first have a kind of like large range model, you try to see they can generate the visual layout. So basically I take this tag and add the model to see which is the layout only of the object entities in the thing. And you can use this to ground the generation. You can use this layout to ground the generation so that you get better aligned image generation. All right, so but it's still not. I mean, we tried this approach, and we still find it's very not satisfactory with the current result. So we tried the different aspects, counting, composition, and color, and size. And what we found is that if you just use the existing use ChatGPT and then actually find pretty understand the visual layout quite well, they can generate powerful polynomials that describe all the objects and their spatial relationships. So this is very good. But the problem is that the grounding text image that doesn't work out well. Still, you see the incorrect object count and missing out object, and the color is kind of messed up, and then some of the objects you mentioned in the prompt, they're ignored. Right. So, and we present a method that try to we'll put it in a CPR one thing is that we will be able to fix all this issues without going over the training process again. Okay. All right. So briefly we have the different model. Basically, different model is a way to kind of generate number samples by iteratively removing noise from the image. Okay, so it's not important about the math here. So basically, once it's the case, like you have a text form, and then we want to generate the image, you'll go through the process and then iterate over multiple times, and then you'll get an image like this. So the problem is that you can see that we're trying to test the functionality of the image, like of the model. You see that there's the horse and dog, but there's no dog here, right? So why is this dog? And the reason why is that most of the text image generative models, they use something called process engine, right? So let's try to recap like what process engine is and then how we can fix it. Right. So process engine basically try to essentially inject textual features into the image. So they kind of mix them out so that your images are kind of, and you can drive the image generation through text. Right. So we start with one layer, some features, and a sequence of text tokens, like a photo on the left of the dog. And so you basically extract the query features from the image and then key and values from the text. Right. And then you do the meta stuff. You can kind of vectorize it into a giant vector, and then you compute the correlation, the addition matrix, you get a key and values, and then you get a process into map. And once you have this, you can use this to basically tell you how features that relate to your query text, and you can use this to kind of compute weighted average of the text value feature, and then create a new feature, and you can add it back to the image. That's how you can figure things out. Right. So it's very interesting to see how we can kind of visualize what exactly where is the text information gets injected into the image. So you can look at this, right? If you look at the composition map, if you specify a particular token, let's say the horse token or the dog token, you'll be able to kind of reshape it and back to the standard size change. And this was what the horse token is doing, right? So you can see basically what it shows is that it tries to kind of inject the horse features and the features into these features, right? And you can look at the same thing like a speed here. Like you see that the horse, the dog features actually are in the right location, but the horse feature gets mixed up. So maybe you at the same location you will see some features from both horse and dog, so the model gets confused, don't know what to do, and then just generate to solve the story. Right. So how do we fix it? So let's say we already have the visual layout from the large language model like this. So what we can do is that we just kind of force this internet to behave correctly. Right. So for example, I have this horse bounding box and dog bounding box. So what I need to do is I will just make sure that the patient map, we think the bounding box is higher and the correct associated with the correct operation is higher, and the outside region is kind of subtracted. It's very, very simple. And what's cooler is that you can formulate this as an objective function, and that objective function is a differential with respect to the image feature at t, which means that during the sampling, you can actually take a gradient step. It's not about training the model, it's like gradient step with respect to xt, and that you can train it. Okay? You can basically, during the sampling, you can nudge the model so that you reach the classification map to have the consistent effect. Okay, so that's how we can do this. And we also do something, so this is about classification. We look at the classification map. So this is a way to kind of refine its own feature by looking at contextual keys. So similarly, you have image features, and you grab query key values, and then you kind of compute a query and see and get a process classification map. And then use this attention to get the values, and then so on. So it's very kind of straightforward. Similar to classification map, but it's kind of easy itself. So if you look at the classification map, you can also get something like, suppose I have a query point from the forest location, and and then you reshape this thing back to a 3D image, and this is what it looks like. So basically, you can think about I'm trying to refine the features of the forest region using the forest region. Look around and see how what other features look like, and then how we can define it. But you can see that it also has other random location features. So it's kind of that's why we have this kind of object mixed up problem. And we will say that okay, you can just say that you can formulate a lot that penalize the rotation weight outside the box, and then you can get better results. And then you can also formulate it with the function, so you can take this and do this cycle. Right. So what's cool about this is that you can take this and this attention proposing that this is you can plug into any model in a plug and play method. Okay. So here we show some examples that if you kind of take division, multiplication, layout, and so on. So test them, put the limit on the conditionality, and you will find that it's not really kind of getting the correct answer. And but you can just plug in our answer, you just fix all the problems. So it's kind of like a add-on that can apply to any of these answers. Right, and you can we will kind of quantify this. Everyone you got a lot of tables, so you have tables. So you can see that across the board, then you get improvement over the. All right, so and this does not suffer from the diversity as well. You can still generate diverse samples. All right, so let's go a little bit faster. Cover some of the later parts. So in an extended to region-based, like on component, you can have some ages, depth net, some folio duration. But you see that it still suffer, even with this kind of guidance, still suffer from mixing up if you test on something that's more requires some regional reasoning. And with our region-based guidance, you can fix all these problems. Right? All right, so this framework also provides a very intuitive way to do instruction editing, for example, if you can add or can, like that is something. Because all the thing is like grounded. So it's very easy to it's not a black box that you have to interface with the textual experience model. Okay, so you can easily do this editing. All right, so the problem is we have a result thing, so we use a large range model for figuring out the functionality, how we can figure out the layout. And you can use that, you have a training method that model of something, and then can do all the functionality. So hopefully this will later will be useful for generating a more precise image. All right, so this is about single images. Let's talk about a little bit about like multi-images. So multiple images being like a pretty popular these days. Like there are many different contexts. So people starting with video generation, they want to generate images that are consistent with each other. Want to generate like multiple images so that they can control the speed. You want to generate a consistent style that can be visual appearance, or generate like a character. And so look at this landscape. So one thing we are particularly interested in is to look at how we can deal with consistent instruction generation. So I look at the WikiHow, there's lots of like people ask a lot of questions about how to use the stuff. But most of this kind of instructions and also kind of many different places has all this platform. So people love to learn how to do stuff. But most of these kind of things do not have the images. They don't have text. So I was thinking about like maybe it would be pretty cool if we can kind of visualize the text, we can augment this instructional knowledge with the text, in the text form. So let's see how we can do this. So if we just use like say, a very simple task like make a something note, and if you just use the independent generation, what you'll find is this process. So you'll see that kind of these images. All right. So individually they look fine, but if you but in the collection, it doesn't make any sense, right? So you see a lot of like confusing results. For example, you see that previously was in a steel part, but now suddenly it's become a black hole. And with property, the milk disappear. So it's very hard to get this kind of consistency across the project. Okay, so let's try practice before. So you see that they kind of the style is the same, but all you see that all the kind of background is just flickering, and then they still is not like first like performance across the thing, so that you don't know what is changing, what's not changing. Right. So what we did is that we can generate, we can again use the training free method and then allow us to generate the consistent generation across multiple steps. The interesting part is that it's not just only about consistency. It's not just saying that I want to make sure that the orders are consistent, but because when you do certain instructions, you will change the state of the thing. So over the state, you will change the state of the thing. So you need to balance between when you preserve the consistency, but also you want to change. So that's kind of the thing that's hard about it. Okay. So because it's zero-shot method, so you can actually apply this to a variety of different tasks. Unlike a existing method, they usually have to spread on particular cooking tasks. Like if you have data set, you have spread data set. But because you have the zero-shot method, you can use it to generate consistent results across the thing. All right, so a few words about the kind of the main idea of this method. The main idea of the method is very simple. Like if you just use the independent variable, this doesn't make sense. But if you that looks like this, just you put a calculator there, but we didn't mention that there's a loop in the font before, so it kind of doesn't make sense. But if you just concatenate these things together, if you take the action and just generate a longer caption, and it also doesn't make sense to just generate the whole thing, putting a middle inside a box. So this is like the question I had earlier, like you import consistency, but it doesn't, if you want to change the flaw. So what we did is that when you do the instructions about the action, you also want to make sure that you ask ChatGPT or some text model to produce a state description about the thing, and that will give you a better score. Okay, so that's how you can get it. Right. So this is about how you capture information, and we also try. Another aspect is that you want to do some attention sharing that somebody can use the original model. So if you share all the way, you get a very consistent result, but does not preserve that particular step. So what we do is that you can do this adaptation. Okay. So first there's some indication, for example, the quantification, like the quantification is not raw, and the void get is not correct. And the most annoying thing here is that the generative, I have no idea how to make it from this instruction. So it looks like this thing. Like I was one thing I was like, they just put it in and then just throw away. Like so it's really annoying. Like so still a long way to go to generate like a very long step and make sure that it comes. But I think it's a very important question. It's very interesting application. All right, so and then I want to kind of highlight the students behind this work. So Ben and Songwei, and I would like to thank you for your attention, and I'll be happy to take any questions. No, 2 minutes done. This is not wrong. This is stable. You can do that, and we kind of bypass that the benchmarking model. But you can just test. You don't have any to tell you just test, but you just as a next model to figure out what the possible spatial layout is. All right, thank you.
Okay, hi everyone. Thanks for inviting me. So I'm going to talk about learning vision without visual data. And this is work with a bunch of students, as well as Antonio Peralta, another PI who's really been pushing in this direction. We've been working on it together. And another way of thinking about this line of work is a lot of folks are trying to build bigger data sets, billions of images, n goes to infinity. We want to do n goes to 0. No data, no visual data at all. Okay, so this is like blasphemy, but let's see if it can work. Okay, so this is the standard way we train our systems. We're in the era of big data, machine learning, computer vision. It's all about the data. And one of the big successes of the last 10 years was that we got rid of the labels. So we used to train classifiers to label images. And now we do self-supervised learning, and we do pre-training in various forms. So we got rid of the labels. And in this talk, I'm going to say, what about, let's get rid of the data too. Okay. Okay, so it sounds crazy, but there's a little sleight of hand here. So I'm just going to redefine what counts as data. So I want to say we're going to be learning vision without visual data. We're going to be using some kind of data. But what do I mean by that? So what do I mean by visual data? I mean things that look like photos, pixels, actual photographs online, outputs from generative models which are realistic and trained to imitate photos, like Stable Diffusion, computer graphics, which makes renderings which look like the world that we see. Okay, this is visual data. What is not visual data, and what we're going to look at in this talk, is language. Okay, but there is a little sleight of hand, because if you read this passage, this is from Proust's description of the Madeleine dipped in tea. It's a famous passage, and it's very evocative. It's very visual. There's a lot of imagery that's described in other senses as well, like taste and memory. Okay, so maybe this is a bit of a trick where I'm kind of pushing visual information in through a different modality, and that's actually going to be one of the points. What about code? So code, also I'm going to say, is not visual data. but code can render to images. There is code underlying computer graphics, but short little snippets of code that we'll look at in this talk, I'm going to say, are not visual data. Another one that's not visual data is going to be math, just equations. But equations can describe the visual world as well. Okay, so this is my working definition for the purpose of this talk, but you can decide how you want to define it. Okay, so I'm going to go through a little snippet on each of those 3 types of other ways of training computer vision systems. So the first will be learning vision from just equations, or in the past, we would call this learning, we phrase this work as learning vision from noise, simple equations that describe noise processes like Gaussian noise or fractals. Okay. So the motivation for this, this first piece of work comes from this observation that neuroscientists have made that in the developing retina in the fetus of mammals, you get what are called retinal waves. So let me show you what they look like. This is a picture of the retina of an animal in the womb. So there's no light activating that retina, but it's spontaneously being activated by kind of top-down stimulation from the brain. And it looks like random patterns, gratings, sinusoids, moving blobs. And what neuroscientists think might be going on is that this is acting like synthetic training data to train up the visual cortex in the animal. So that when it's born and it first sees light, it can already make sense of it. It already has some oriented filters and other simple structures. Okay, so we took that as inspiration. And a few years ago, we tried to design our own retinal waves for computer vision systems. And we made processes that look like this. And this is work that was led by Manel, Jonas, and Tongzhou. Okay, so throughout the talk, the kind of basic computer vision learning system is going to be self-supervised contrastive learning, because it can be a little bit confusing. How are you going to learn a system on noise? What about the labels? What is the task? So this is going to be the entire task. We take some kind of data we make, in this case, this random noise kind of Gaussian clouds, and we generate 2 crops from that noise, and we try to classify, do those 2 crops come from the same image or different images? So this is standard contrastive learning of the kind in SimClear or MoCo or any number of other works. Okay, so that we're going to try to train systems using that method, and our only design choice is going to be what is the left side input? What is the data that we're going to put into this system? That's our entire design space. Okay, and how are we going to evaluate if that system that we trained, so this contrastive learner trained on some data process that looks like noise here, how are we going to evaluate it if it actually learned a good visual representation? We're going to use transfer learning. So again, a very standard setting. We're going to pre-train on some data, in this case, noise, and then we're going to evaluate performance on a different data set by fine-tuning, or in this case, linear transfer. So take the features of the model F and try to linearly classify ImageNet 100 categories. Okay, so the very first thing you can do if you're going to try to learn vision without any data, any images, is just say, well, what if I just randomly initialize a neural network? I don't even feed in any images into it, right? Okay, so how well does that do if I do linear transfer from a randomly initialized convolutional network or ResNet? This is a few years ago, so we're in the ResNet era. Okay, so it's actually not that bad. This is one of those surprising things for us from about 5 years ago, that random networks can do all right as a representation of visual data. On a 100-way classification task, you're at 20% accuracy. But it's pretty far from how well you would do if you actually trained on real data. So training on real data is going to kind of act like an upper bound, and not training it at all, just random initialization is kind of a lower bound. We're going to try to bridge the gap between these two things. So if I train a system on the places data set, I do linear transfer to the ImageNet data set. In this particular setting, we get 55% performance. Okay, this is not a state-of-the-art setting. This is more a scientific kind of exploration of what noise processes can bridge that gap. Okay. So also as a kind of starting baseline, let's look at the nearest neighbors in representation space from a randomly initialized convolutional network. On the left here in the column is the query images, and on the right are the k nearest neighbors in some data set. And so you can see that the nearest neighbor in this representation, which is a random representation for a lobster, they're red things. It got in color. Like, this is the thing. Random networks are not trivial. But okay, got one lobster. Actually, that's pretty cool. But most of the semantics are just completely off in this case, and the accuracy of a nearest neighbor classifier would be 4%. Okay, so let's design some noise processes. Okay, the first, we're going to start really simple. They're all going to be simple, but the first one is going to be just 1/f noise. So this is a remarkable property of the visual world that the power spectrum follows this kind of 1/f distribution. And we can take random white noise on the left. We can do a Fourier transform, impose this 1/f power spectrum, do the inverse Fourier transform, and we get 1/f noise. So this is what we are saying. We think that the visual world looks like up to this particular statistic of the world. So it's our proxy for the visual world, but it's a simple equation that gives you that proxy. Okay, so how well is that going to do? So you can start to guess. I'll show this plot a few times, where's it going to lie, right? Okay. Okay, so somewhere down here. It's pretty simple, but that's kind of interesting. You can already get a 10% boost over a randomly initialized network just by kind of training it on 1/f noise. Okay. But we can make it more complicated. We can not only do 1/f noise, but impose some kind of color spectrum that it matches natural statistics, and we get a little bit better. I'm not going into the detail of each of these methods. The next big one that we looked at is the dead leaves process, another simple model of how the visual world works. Again, you can write this in a few equations or maybe a few lines of Python. And the way it works is you just splat down squares or rectangles and overlap them. It's supposed to kind of capture the fact that the world it consists of overlapping leaves or occluders that layer on the ground. Okay, so here's what the training data looks like with this process. We can also use oriented shapes, or we can use circles or triangles or a mixture of all of those things. And each of those different processes leads to a slightly different performance, but the gist of it is that as you add a little bit more structure, you add oriented shapes, you add circles and triangles, you start to edge up closer and closer to what you would get if you'd actually trained on real photos. Okay, but these are still very simple processes. Okay, another one that we looked at is what if we take a generative model of the era, StyleGAN, and rather than training it to make realistic photos, we just randomly initialize StyleGAN and use it as kind of a image prior, kind of a noise generator. And if you randomly initialize StyleGAN with nice filters, just simple, Gaussian filters of various forms, then you get these kinds of images here. Okay, so there is in the architecture of these generative models some inductive biases that cause them to make things that we would recognize as kind of image-like, look a bit like natural images. Okay, so that one, we have two different forms, and if you choose oriented filters rather than isotropic filters for your initial weights, you get actually a pretty good performance. We're starting to get close. But I think it's more evocative to look at it with the nearest neighbors. So here again is that same, the nearest neighbors in a computer vision system trained only on random images of the kind that StyleGAN at init generates gets matches like this. Okay, now four of the neighbors of the lobster are lobsters, and one of the lorikeets was matched as a lorikeet, and the birds are matched as mostly birds. Okay, so again, this is a system that's never seen a natural image. It's only seen these StyleGAN random patterns, and it gets 33% accuracy under this nearest neighbor metric. Okay, there's a 100-way classification problem, so 33% is non-trivial. Okay, so that's as far as we got with kind of simple equations and I guess noise or math. And we then thought, well, okay, if StyleGAN's doing this well, it's a little bit more complicated. Could we come up with even more complicated, but still procedural and kind of randomized generative processes, not fit to natural images? And the one we looked at next is code. And in particular, we looked at code that is in the form of these shader programs. So the way to think of this is kind of what is the shortest program that yields vision? We have a short program for taking an image data set and training a model on it. That short program is called backpropagation in PyTorch and all the rest. That's a very short program. But the data itself, ImageNet, Lion, these huge data sets, they're not easy to describe with only a few lines of code. So could we instead describe the data generating process with just a few lines of code? And so we use these programs, these things that people online like to compete over in this demo scene community. They try to make really short programs that generate complex visual experiences. Here's a tweet that generates under the OpenGL shader language, the movie on the right. Okay, these are really fun. It's cool artistic endeavor. And we explored that in this paper on procedural image programs for representation learning, and again with Manil and a few other co-authors. Okay, so we collected 21,000 programs of that kind, all made by humans online. So there is, data coming in through the human artist, but it's not visual data as pixels or photos. And each of the programs is only a few hundred or thousands of lines, thousands of characters, so very short programs. Okay, so they look like this. Take a look online if you're interested in this area. It's really amazing how much a few hundred characters can get you in these shader programs. They get, it turns out that the programming language itself has some primitives for 3D rotation and camera optics. So that's another little sneaking in of information, but still these are simple programs, and like the cosmographic complexity of the system is quite simple. Okay. So how old is it? What do you think? Okay, I left it blank. It's probably gonna fill that blank. Is it gonna go all the way? Almost, okay. So we're pretty close in this particular setting to finding a way of training on synthetic processes not fit to any real data explicitly, and yet getting close to matching if you train in real data. This is not a state-of-the-art transfer learning setup with the biggest nets or anything like that. So that gap will get bigger if you move to more powerful models trained on more natural images. But it was the setting in which we got close. Okay. The nearest neighbors, let's see how they do. This is nearest neighbors of a system trained on shaders. Okay, it's almost perfect now. Like, this system has never seen a real photo. It's seen those weird movies that it's just showing you, and yet two lorikeets match two lorikeets. This guy eating lobster matches to a guy eating lobster. That's the nearest neighbor in the ImageNet 100 dataset. Okay. You might be interested, if I could only train on one shader, what would be the best shader to train on? And here it is. So this shader, if you watch this movie, your brain is going to be pre-trained. And if you then do a linear transfer to ImageNet, you'll be 36% accurate. So you can go and do that after this talk. I don't know about that for the brain, but that's the fact for the model. Okay, so that program is telling you a lot about how ImageNet works, or at least giving you the right early visual filters that lead you to good performance on ImageNet. Okay, so time check. I have one more section to the talk. Okay. So the last section of the talk will be learning vision from language. And this is, a large language model can read all these visual descriptions. Does it get a knowledge of the visual world? And this is work that will be presented later this week at CVPR, a vision checkup for language models, and it's led by Pradyusha and Tamar. Okay, so we looked at two questions, or a few questions in this paper. One is, can language models draw? And two is, can they see? Let me emphasize that these are language models. They're not visual language models. These are the kind of language models trained only on language. Okay, we have some results with GPT-4. It's not quite clear if that's also sneaking in images, but ignore those results if you prefer. Okay, so can language models draw? So I'm sure you've all seen the unicorn example, a million examples of this over the last year or two. And so yes, so here's how we studied that. We say, prompt the language model, give me processing. Processing is a programming language that renders images. Give me code and processing that will draw men herding sheep. We put that into the LLM, it outputs code, we render the code with processing, and you get a photo about these people herding sheep, or a rendering of it. So this is like the unicorn Tixie, if you've seen that. Okay, but we kind of made a big data set around that, trying to assess the performance of these models on rendering shapes, colors, textures, scenes, objects, and so forth. So if you're interested, there's some details in the paper about which ones do well on that problem. But the basic fact is they can do all right. And I think that we know that now. People know that. What's a little bit more interesting and new, I think, is, can language models see? So we can do kind of the opposite direction. We can have humans draw scenes like the men herding sheep and processing. So humans on Mechanical Turk will draw scenes like this. We'll extract the code that matches their drawing, because the drawing interface is made of primitives, and we know the code for each primitive. So we know that this drawing of the bicycle is 2 circles at these coordinates and so forth. But a human made this, not a language model. And now we can give that code as our visual description of the scene to a language model. It's now in a format it can process, and we can ask it, what is this? Is it a bicycle? And we had humans on Mechanical Turk draw a lot of scenes like this. Okay, so they have simple prompts like draw a strawberry, and they make this kind of funny looking strawberry. They're pretty good. They're not quite as good as the LLMs at drawing scenes, but they're okay. And we can now ask, can a language model understand those images when represented as the code that renders them? So here's the human drawing, and we prompt the language model, what does the following code represent? And we give it the code that matches the human drawing, and then we give it a binary task. Is this a lake next to a terrace and with traffic lights, or is it a sandy beach? I guess it's a 5-way classification task. Is this a lake? Is this sky? Is this a terrace? And so forth. Okay, it's a 5-way classification task, and it says that's a sky. And if it says that, then we give it +1, and we measure accuracy. Okay, so how does it do? Okay, you're probably expecting me to say it's amazing, right? No, it actually is barely above chance. So chance is 20% accuracy, and here are a few language models. I think interestingly, GPT 3.5, which we're pretty confident is not trained on visual data, gives 38% accuracy on recognizing scenes drawn by humans in this way. Okay, so not zero, but there's a long way to go. But when it's wrong, it's usually okay. Like look at this one here. A human drew this terrace. They tried to draw a house, but with a fence. But the language model said, I think that's a staircase. But to me, it looks also like a staircase. So the errors are reasonable. We have more examples on the website if you're interested. Okay, the last thing I'll show is, can we train a vision model from the images generated by a language model? So it's the same setup as in the first sections of this talk. We're going to sample a lot of images drawn by a language model. That's our new training data set. We'll do contrastive learning on them, and then we'll transfer to a classification problem. And the answer is, this can also work decently well. Okay, so here are the 5 nearest neighbors to a system trained only on language generated renderings, and it's never seen a real photo. It's only gotten the knowledge from the language model, and it can recognize or at least match a lorikeet to a lorikeet. Okay, so to conclude, this n = 0 setting, no pixels, no real photos, no synthetic images that are photorealistic, seems to be possible. I think it's an interesting setting. You can learn from math, you can learn from code, you can learn from language, it can transfer to vision. Can you learn from anything? And I'll just give a little pitch at the end that we have a position paper where we're basically saying, yes, you can learn from anything. All these types of data are projections, reflections of the world. They're all connected in some way. So maybe look at using other data that you normally wouldn't think of as visual data to train computer vision systems. And I'll end there. Thank you.
So we have time for one question. You can use the microphone.
Reasonable results. I guess the alternative hypothesis that comes up when I see these results is it that shaders, for instance, are really amazing at mimicking these visual statistics, or is it just the fact that image classification does not require that much beyond being able to model long-range variation?
I think that's a great question. You could phrase it as, is vision actually easier than we thought it was? Maybe it turns out that all these things we thought were really hard, like recognition, that we thought, oh, that only works with big data. It turns out, actually, it's not as hard. And maybe small data can actually do it if you do it in the right way, or small information in a sense. So I think that's an open question. And maybe these results won't hold up as well for more fine-grained tasks. Yeah. Okay, thank you.
Yeah, thank you.
see my screen. Hello, hi everyone. I'm Tali. It's a great privilege to be here. And today I'll talk about the huge revolution that we are witnessing in generative AI and specifically in video generation. So models in this domain require a tremendous amount of compute and training data, but I'm hoping to convince you today, building on my own work, that the future of video generation goes way beyond just data and scale. And I'll show you what we can do in an academic lab without tons of GPUs and without tons of data. So just to say, this is going to be more of a high-level talk, but I hope I'll have the time to also dive into technical details towards the second part of the talk. So the generative AI revolution has recently expanded to videos. We can now not only generate mind-blowing images, but we can make everything move. So all these videos are AI generated. So given this exciting progress, we can start to envision how film production may look like in the near future. Maybe we'll be able to produce films completely computationally using simple text prompts. Maybe we can ask ChatGPT to write a script for us like this. And then it may generate the movie for us. And then we may ask it to add some special effects like a bullet time effect, and it will just generate it for us completely computationally without any real actors or cameras, just using generative AI. So the truth is that we are quite far from it. And despite all this amazing progress, even state-of-the-art models like Sora still have weaknesses, and they still depict very fundamental failure cases. So for example, they may struggle to accurately simulate the physics of objects. Like in this example, the item that is pulled out of the sand is supposed to be a rigid chair. And Sora seems to fail to simulate that. Or in this example, where the treadmill is following the person in an unrealistic manner and moves along with it. Or in other scenes that involve multiple entities, objects tend to spontaneously appear and disappear, then go inside each other. Furthermore, the cost of scaling up video models is just huge. One instance of model training requires roughly about 200K GPU hours, which amount to roughly $280K dollars. And in terms of energy consumption, generating half a second of a video requires the amount of energy needed to drive 4 miles on an average car. And because of these huge costs and compute requirement, designing such models is restricted only to a few big players in industry. And more importantly, even, if we go back to our moonshot goal of producing films computationally, we're going to need some fine-grained controls, which is not provided by these models. We may want to accurately control the camera position, the characters' identity, their emotion, their movements, the scene geometry. We may want to control lighting and sound and speech. So at Google, I had the privilege to design video foundation models, but actually my my research journey in the realm of video synthesis started from the other side of the spectrum with single video models. And what I mean by that is that we have neural networks that are overfitted and observed only a single test video. They do not know anything about the world except this single video. And we showed in a line of works. 1, 2. No. It's very surprising when it suddenly stops. Okay. Can you hear me? No. Again? No, no.
Hello.
to have like this mic, maybe.
Hello, hello.
Can you hear me? Try to speak louder. Okay. So what I mean by single video models is that we have neural networks that are overfitted and observed only a single test video. And we showed in a line of work that actually single video models can unlock some pretty impressive capabilities. So for example, consider this busy scene. We can remove all the people except the desired one from the scene. And you can notice how we are not only removing the people from the scene, but also all the complex scene effects that are related to them, like the complex deformation that are caused to the trampoline. This is a video of my son riding his bikes for the first time, and we could make this video much more memorable by stylizing the background, and you can notice how everything moves consistently with the original video. And we can also map texture onto deformable objects like the flower on the dress in this example. And again, this is all obtained with with models that only observed a single video. Of course, their main disadvantage is that they don't have any prior information and knowledge about the world. But the key property of them is that they can allow us to go way beyond just representing a video through a huge pixel volume. We can devise new smart, effective video representation that can unlock these capabilities. So for example, in layered neural atlases, our key idea was to take an input video and decompose it into a set of canonical 2D images. So you can see here we have two images, one that represents the entire background of the video and one that represents the foreground object. And each position in the video is being mapped onto these 2D images. We also predict the visibility of the foreground versus background in each pixel. And this representation allows us to reconstruct the original video. And what's nice about this representation is that it really simplifies the task of video editing. Now, instead of editing a huge pixel volume, all we have to do is to edit a single 2D image, which we know how to do very well. We can just load these images in Photoshop, add some colors onto them or edit object, and then use the learned mapping to map it back to the original video completely automatically without any effort. Okay, so just to recap, I talked about video foundation models and their disadvantages in having huge costs, limited accessibility, and limited controllability. On the other hand, because they are trained on video data and they observe our dynamic world, they can learn these powerful space-time priors about the world. On the other side of the spectrum, we have the single video models. They only require few GPUs to train. They are accessible and they can allow us to gain explicit control over the content. However, they have no prior about the world and no knowledge about how things behave in our dynamic world. So in both Google and Weitzman, I was working on both of these models, but moving forward, I think the way to go is actually to combine these two ends. And what I mean by that is that we still want to have a model that is tailored to a specific test video and will allow us to devise a smart representation or to capture the unique dynamics that appears in a single test video. But also we want to fuse this representation with external priors and knowledge that is learned by large-scale foundation models. And these large-scale foundation models can be different models that can give us different priors. So we might want to incorporate motion priors or geometric priors, generative priors, and semantic priors. Can you guys hear me? Yeah, on the back. Cool. Okay. Yeah, so my first attempt to take a step into this direction to pursue my goal was text to live that was presented in ECCV. And this was the first method actually to show text-driven editing to real-world videos. And the key idea there was to use a pre-trained neural atlas representation, sort of like a video render. So again, I remind you, this representation is overfitted to a single test video. We obtain it. And then the key idea is to replace the manual edits that I showed you with text-driven edits that will be applied automatically. In order to achieve that, we combine the neural atlas representation with the external priors learned by a clip, by clip. And this allowed us to, again, perform these localized and semantic text-driven edits to real-world videos for the first time. Okay, so one of the main challenges in pursuing this goal of combining these two ends of the spectrum is that current foundation models are mostly treated as black boxes. We do not fully understand them. We do not fully understand the priors that they learn and how they are internally represented. And this poses the challenge, how can we distill these learned priors from these black boxes? So in the time that I have left, I want to actually dive into a line of works that aims to really dive into the internal representation of large-scale models and gain a better understanding of their internal representation. And I'll show you that if we gain this understanding, this opens up the door to developing very lightweight methodologies that requires no training and minimal adaptation. So in text-to-live, we use clip, but this was before stable diffusion came out and so on. And with the rise of the text-to-image model, we suddenly have this amazing capability to generate very complex visual signals. So as evident by generated images, we can see that those images depict composition, pose, interactions between object, texture. That means that text-to-image model, they learn all these priors in the process of generating images. And I was really intrigued by that, and it got me excited about how can we take text-to-image models and expand their capabilities, distill their priors beyond what they are meant to do, beyond just generating images from text. So in my lab, we worked on different aspects of this goal. In the beginning, we showed how can we take text-to-image models and gain spatial control, different spatial controls over the generated content. So for example, in plug and play, you can see that we can preserve the semantic layout of a given input image while editing it in a way that keeps a high fidelity to a given text prompt. And in multi-diffusion, we showed how can we expand text-to-image generation to generate images at arbitrary aspect ratio, and also for providing region-based text prompts, as you can see here. But related to videos, again, I was really intrigued by this question of how can we use the text-to-image priors for video synthesis tasks. So in Synscape, we showed that you can not only generate nice, beautiful scenery from text, you can actually generate a 3D consistent walkthrough inside those scenes by coupling text-to-image with depth priors and explicit mesh representation of the scene behind the hood. And in token flow, we showed that you can not only synthesize static scene, you can also edit dynamic scenes using simple text prompt, using a text-to-image model. And again, I think everyone are using text-to-image and adapt it in various ways. I think what's unique about this line of works is that, again, in our setting, the text-to-image model remains fixed, and it doesn't require any fine-tuning or additional training data. And this is achieved, again, by pursuing this approach of diving deep inside the model and understanding how things are internally represented. So let's dive in a bit more into token flow, which was presented in last ICLR, and it's a work led by Michal Geyer and Omer Bertal from my group. And again, our goal was to edit real-world videos in a consistent manner using simple text prompt. And we started off with this simple baseline of just applying image-based editing to each frame independently. And as you can see here, you can see that the consistency breaks, and it's not just like high-frequency flickerness. the content is changing dramatically from one frame to another. And really, there is no reason to believe that just a text-to-image model will produce something consistent. So we wanted to understand how these inconsistencies are being represented inside this model, and that brought us to analyze the diffusion features across different frames. And the way we've done this is that you take the input video, you can invert it into the pre-trained text-to-image model using DDM inversion. Again, each frame independently because it's a 2D model. So we can invert each frame and extract some features, and then reduce their dimensionality using PCA. So here you can see the PCA visualization of different features across different unit levels. And what we can observe is that the internal representation exhibit this shared and consistent representation across frames. So we see consistency in RGB, and we see the same level of consistency in the internal features of the diffusion model. And we looked at this shared representation in a finer grain manner by looking on nearest neighbors. So we can take just one token or one feature for one frame and compute its nearest neighbors in other frames. And those nearest neighbors showed to capture these semantic and accurate correspondences across different frames. Okay, and we can compute this nearest neighbor field densely. So each feature in one frame will compute its nearest neighbor in the other frame, and that gives rise to this nearest neighbor flow field, which we named token flow. And now let's see what happens under this naive baseline. So again, we've seen that for the original video, we get consistent features. But once we apply a per frame editing independently, this consistency breaks. And that suggests that there is a tight connection and relation between consistency in RGB space to consistency in feature space. So our key idea in token flow was that we can achieve consistent video editing by enforcing consistent feature representation on the edited video. And more specifically, we want to enforce the original correspondences between features of the original video on the edited video. We want to enforce the original token flow on the edited video. And the way we've done this is using this framework. Again, I'll describe it in high level, but in the first step, we take our original video, we invert it into the model, we extract the tokens and compute the token flow. And then during the editing sampling process of the edited video, we iterate between two stages. In the first stage, we sample keyframes and jointly edit them using extended attention. And this gives kind of like a global shared content among the keyframes. We extract the edited tokens and then propagate them to the rest of the frames using the original token flow that was computed from the original video. And we repeat this process. So here you can see some editing results. And again, you can see that the consistency is pretty nice, given that we are only using a text-to-image model that never observed the video and was not fine-tuned for this task in any manner. Some comparison to baselines and competing methods. Some are tuned on a single video, and some are feed-forward kind of like video models that also receives a depth map like Gen 1. You can see that our consistency is much better. Okay, so text-to-image models are amazing, but if we really want to model our dynamic world, we need motion priors. And this is something text-to-image models cannot provide us. We need priors about how things tend to move in the world, their dynamics, and I wanted to move beyond just having 2D priors. And again, I remind you that even the existing text-to-video models are still not perfect. They really, they observe tons of data, tons of videos, and they can encode powerful priors about our dynamic world, even if the you know, the pixel quality is not perfect. Okay, so that brings me to the last work that I want to discuss today and show you. It's a paper that will presented here at CVPR. And again, the motivation is, again, film industry, you know, where they put a lot of effort in transferring motion from actors that are wearing those markers to creating these CGI effects and transferring it into new objects, like you can see here. So we wanted to achieve this, to be able to transfer motion from one object to another completely computationally, like you can see here. So the input is a driving video. And we want to transfer the motion depicted in this driving video onto different object categories using simple text prompt. And you can see that in order to achieve this, we must allow flexibility. We are no longer interested in preserving pixel level correspondences because the shape of the new objects must change in order to convey the new object category. So we need to kind of like distill the essence of motion from the original driving video and being able to adjust the shape and the fine-grained motion characteristic in order to generate a plausible target object. And in order to do that, we must have a prior about how things are moving in the world. So in order to achieve that, we use a pre-trained text-to-video model, specifically ZeroScope, and you can see some sample videos from this model. Again, very far from state-of-the-art, but we found that still this model can learn very valuable priors about our dynamic world. And just in terms of how we define motion for our task, again, no longer interested in pixel level correspondences. In our case, we kind of like treat motion as a sequence of semantic parts positions. So we can think about an object as being kind of like divided into semantic object parts, where each part we think about its general position. And that's the thing that we want to preserve here. It's more of a semantic definition of motion. And prior work is really not designed to allow such deviation in shape and structure, as I'll show next. Okay, so following token flow, we took a similar approach of diving inside the text-to-video model and trying to understand how space-time information is internally encoded inside the model. So again, we can take a video and use DDAM inversion to invert it inside the pre-trained text-to-video model. In this case, the extracted features are f by m by n d dimensions. So f is the number of frames, n and n are the spatial dimensions, and we have d dimensions. So each frame is being represented by m by n by d tensor, okay? And now, in order to gain a better understanding of these features, we adopted this technique of feature inversion that was originally suggested in the context of understanding classifiers. So very briefly, feature inversion. In feature inversion, we have a pre-trained model, and we have some input. We feed the input inside the model. We extract some target features. And now, in order to understand what these features encode, our goal is to solve for another input, to optimize for an input, such that when we'll fit it inside the model, we'll obtain the same matching target feature. So in our case, we took this video of a woman performing jumping jacks. We inverted it into the model, extracted features, and now our goal is to solve for a new video such that when we will fit it into the diffusion model, it will give rise to the same space-time features. And you could do that using guidance, where you optimize for xt at each given diffusion sampling step. And here you can see the feature inversion results across different seeds. And as you can see, just matching those features gives rise to pretty accurate reconstruction of the video. So we reconstruct the motion, the background, the appearance, and so on, which is not good for our task because we want to allow flexibility. So we want to have some descriptor that will preserve the essence of motion and the general pose of the object, but will be robust to appearance changes and structural changes. Okay? So aiming to reduce pixel dependency, what we've done is we took those features and basically just collapsed the spatial dimension. So we call these features spatial marginal mean, or SMM features. Basically, it means that for each frame, we have this M by N by D tensor, and we collapse it to 1D dimensional vector. And now we can repeat the inversion experiment with now matching the SMM features and not the full features as before. And as you can see, now we're able to preserve the pose while being flexible in structure and appearance. So we are on the right track to getting our desired descriptor. And this was quite surprising because, again, we collapsed all the spatial information, but still able to get pretty accurate pose out of it. But you should remember that those features lies in this high dimensional space, so they can still capture this information even after this averaging. Okay, so now let's use these features for editing. How will we do that? We'll take our original video, we'll extract those SMM features from the original video, and then use them as guidance during the sampling process of the edited video, okay? So now we are using classifier guidance. At each diffusion step, we're gonna optimize for XT such that the edited SMM features will match those of the original video, okay? And if we do that, we get this result. So we get some flexibility in appearance, but it looks like a camel that was squished into the shape of the elephant, right? So not quite there. So next, what we've done in order to get the descriptor, the desired descriptor, is actually not to optimize directly to match the SMM features, but we basically take as our descriptor to be all the pairwise differences between the SMM features. So we have an F by D matrix where each element here is just the difference between two SMM features. So we basically encode all the pairwise differences between those features, and we're trying to match only the differences rather than the actual features themselves. So again, during the generation process of the edited video, now we are using guidance and with the goal to match those pairwise differences between the SMM features. And if we do that, now we get a nice looking camel that actually that is sync with the original video, as you can see here. Here are some more results. And I think it's really nice to notice here, for example, the bunny's ear. It needs to generate plausible ears that will move in a natural way and to deviate significantly from the cat's region in this example. And for that, you really need a video prior, a motion prior, generative prior to succeed in this task. Here are some more examples. So again, being able to preserve the overall motion in the scene while generating plausible target objects that are significantly different from the original one. And again, compared to existing methods, which are more designed to preserve pixel level motion, they are not able to tackle this task. Just a word on evaluation. So in order to evaluate how much the video is aligned with the text, we can always use clip score. But we wanted to also measure the motion fidelity. And again, because we are not preserving correspondences to the pixel level, we had to come up with a new metric of how we evaluate similarity between the original and target object videos under this misalignment. So we propose to use a similarity between two sets of unaligned trajectory sets. We have the original video and we have the target, the edited video. We can apply off-the-shelf tracker to get a set of trajectories from each one of those videos. And now we suggested to use something like the chamfer distance between these two sets of trajectories. So we are measuring the correlation between each trajectory in the original video to its nearest neighbor in the edited video and vice versa. And this is how the numbers looks like. So you can see that you really want to be on the top right. And our method proposes or gives the base trade-off. You have on the y-axis the motion fidelity score, and on the x-axis the clip similarity score. So you can see that a method like token flow that really preserve the original motion are really high on motion fidelity score, but their clip score is significantly lower. We also tested two versions of SDEdit with different level of noise. So SDEdit, if you noise the original video a bit, you get high motion fidelity, but you're not able to fulfill the edit. And vice versa, if you noise the original video a lot, you can fulfill the edit, but then you won't preserve the original motion of the video. And again, our method gives a much better trade-off between the two. Of course, there are also limitations. So we are bounded by the priors that are learned by the diffusion model. So if the model cannot synthesize, in this example, a squirrel in this pose, our method is gonna fail. Okay, so just to summarize, I guess I talked about the latest in video generation. We talked about the pros and cons of these two ends of the spectrum: large-scale video foundation on one hand, single video models on the other end. I hope I managed to convince you and the potential and effectiveness of combining the best of both worlds. I think there is still tons to be done. We need to think of new ways to represent video content, representation that goes beyond just representing a video as a huge pixel volume. We need to keep digging and understanding and gaining a more profound understanding of large-scale video foundation models and other foundation models, and think of new creative ways of combining the two. I'd like to thank my students that worked on these projects and collaborators, as well as collaborators from Google. And I'll continue to work towards breaking new ground in video analysis and synthesis tasks, and hopefully eventually get to the level where we can generate these really professional high-end effects using simple text prompt and intuitive tools. Thank you.
We have time for only one question. Can you speak louder?
For the single video models there, are they small enough that you can bring it onto device? Just if you're more about the hardware that you're using to make it sound super cool.
Thank you. So we didn't do any optimization to try to optimize the model size or to shrink it to a size that will fit, a mobile or something like that. I think it should be possible. They are quite simple, but most of them are based on simple CNNs or MLPs. And I think there was some work also that showed from Adobe that showed how you can extremely accelerate not only the inference but also the training of such models in a similar manner to what we've seen happening with NERF. Yeah. Thank you.
Thank you. You want to ask? Okay.